This next trend might be the hardest one for you to understand, so hang in there with me as I try to go through it. The ionic radius is very similar to the atomic radius, but instead of dealing with atoms, we're dealing with ions. That means electrons have been lost. In the top illustration, if you look closely, you can see the same trend in atomic radius, between atomic radius and ionic radius, as you go down a column. And that is absolutely what happens. The trend for both atomic and ionic radius is, as you go down a column, the atoms and ions both get bigger. And the reason is still the same. As you go down, there's more electrons, so you need more energy levels, that is, more rings, and there are going to be more of them further away from the nucleus. Very simply put. Now here's where it goes haywire. As you go across a period in atomic radius, you have a very smooth trend, at least in the main group elements, of getting smaller from left to right. As you can see in this same chart at the top of the screen, it is not a smooth trend for ionic radius as you go from left to right across a row. The trend starts out the same as atomic radius, and the ions do start getting smaller. So for example, you see potassium. The potassium one is in the red here, and then calcium's a little smaller. Gallium will be a little smaller even. And then holy smokes, as you get to the P block over here and they start becoming negative, the size just explodes. It goes very big. For any row, the largest ion in that row, in that period, will be the first one that becomes negative. And you're thinking, why in the world is that? Well, when you become positive ions like we have with calcium over here, to lose the electrons, you're emptying the outer layer. In essence, again back to the onion metaphor, you're peeling the outside layer of the onion away. And when you do that, what's left is always smaller. So that kind of makes sense. But why do the negative ones get bigger? Well, in the negative ions, you're adding extra electrons to the valence shell or the energy level that's already there. And you're just filling it up with all it can hold. In essence, what you're adding is more negative charge for more repulsion to the electrons and the inner core that's already there. So they are going to kind of swell. They're going to balloon out from having all these extra electrons repelling and not being very strongly held by the nucleus, because it's kind of like a tug of war. The nucleus has, for example, maybe 10 people pulling in, and the valence electrons have normally 10 people pulling out. Well, if I start adding team members, 12 people pulling out to become a negative ion, then that team is going to win, and the direction is going to move outward to the team that has the more participants. Long story short, negative ions are big, and they are bigger than their positive counterparts on any period or any row. So the trend is a broken trend. We can say that for ionic radius, as we go across a period from left to right, the ions get smaller, and then when they get to the P block, they explode to their biggest negative size, the biggest size for the negative ions, and then they will start getting smaller again. The biggest ion in a row is the most negative. So can we rearrange this to look at it in a more meaningful way? I think so. The answer to this is to use an isoelectronic series. That's going to make us get out of our comfort zone here. And instead of thinking about the trend in ionic radius being left to right on a period, we're going to have to start it instead with an isoelectronic series, where on one side of the isoelectronic series you have the most negative possible ion that contains a certain number of electrons, and on the other side the most positive one that contains a certain number of electrons. The one in the illustration at the bottom of the screen is an isoelectronic series for species that have 10 electrons. Right in the middle of this isoelectronic series is the element neon. Neon always has 10 electrons to match its 10 protons. Neutral charge, but it still has 10 electrons. So that's kind of our fulcrum, our middle. To the left, we go to fluoride ion. The fluoride ion has 9 protons, but because it's -1, it has 10 electrons. That extra electron is going to add repulsion, so fluoride is going to be bigger than neon, who also has 10 electrons. If we go one more to the left, we see the oxide ion. Oxide has 8 protons, but it also has now 10 electrons, just like the other two. 2 extra electrons in that valence shell is going to create even more repulsion. Things are going to spread out even more, so oxide is bigger than both neon and fluoride. If we wanted to predict what would come next, well, you can improve on -2 by a -3 charge, and that would be the nitride anion. It would be bigger than even oxide. Can you guess what would come just to the left of nitride? Yeah, it's the carbon -4 ion. Some people call that the carbide ion. Not totally correct, but that's the trend. And if you saw that, that's good. If we go the other way, heading back to neon, let's go to the right with some positive ones. The sodium ion has 10 electrons as well, because as a +1 ion, it has lost 1. It's only left with 10. And so you've peeled away that valence shell. So the sodium positive ion is smaller than neon. Next, you have magnesium, 2 positive. You've peeled away, again, the outer level by removing the 2 valence electrons, so that one's going to be much smaller. And the effective nuclear charge has increased, so magnesium +2 is going to be even smaller than sodium +1. More protons, fewer electrons. Think of the tug of war. Magnesium's nucleus is really pulling strong. What would come next? Well, if you guessed that next would be aluminum +3, you would be right. Because aluminum, again, peels away that outer layer. You now have 3 extra neutrons in the nucleus pulling hard. Everything is coming closer together. Well, let's summarize the ionic radius trend now. Just like for atomic radius, the trend is bigger as you go down. And then just like atomic radius, it is smaller as you go right. But we have this horrific thing of getting super big right in the middle before we finish off and start getting smaller again. The isoelectronic series is much more useful. Line up all ions and atoms with the same number of electrons, and you'll see a very smooth trend from left to right of getting smaller, starting with the most negative, going to the most positive on the right.